Hello, everyone, and welcome. Today we will be discussing the 2019 free response. But we gotta talk about some other things first. Ugh. Let's see. Ugh. Good morning, Maggie and Zach and Isaac. Hello, everyone. Oh, it's cold this morning. Cold, cold, cold. Yeah, we can. We can. Yeah, we can do some Redox Titration. Ooh, Austin with the Twitch Prime sub. Look at that. I gotta move my alert box down. It's a little high. There we go. Like my sweet alerts there? Streamlabs. Thanks. That's another $2.50. That brings my grand total money making from streaming to like $30. Yeah, so it should do that if anytime anyone follows or donates bits or subscribes or any of those things, should give that little alert thing to pop up. But that's just me trying to make quality. I want to unfollow just to follow again. I don't know if it works if you unfollow and follow again. It might. You can do it. We're not really starting for another 2-3 minutes. Yeah, I'm not sure how that has it coded. It might only like pop up for new followers. Oh, nope. There it goes. It did it. That's funny. That's weird that it doesn't recognize unfollowed and refollowed. What's my daughter yelling about? I need to close my door. They're watching Frozen. They might be at the part where she's like, Elsa's in the ocean. Ugh, and now everyone's pink. So there's something wrong with like the text on my Streamlabs like Twitch chat. Because it like everyone gets stuck at the same color and it doesn't have different colors, and I don't know why. So I guess today it decided that everyone's going to be pink. Maggie, I mean, a donut for breakfast. They like Frozen. I don't know if it's I guess it's their favorite movie right now, probably. Yeah, probably the favorite movie right now. Hi, Naya. Tomorrow's going to be something different. What do you mean, Isaac? Oh, right. Oh, yeah, my kid's new favorite movie. Yeah. No, I got you. I understand. Sorry, it took me a second. Yeah, no, I mean, it changes. I'm sorry, Black White Life. I hope you don't fail. Are you actually in AP Chemistry or in AP class, or are you just being funny? All right. It's 10:05. Let's talk about some resources I put on Canvas real quick. So on Canvas, I went ahead and uploaded the reference sheet that we're working on. I know a lot of people left early Wednesday because it was taking me a lot longer to do the reference sheet. Those are scary nightmares, Black White Life. Isaac, I do play some games on my phone, but nothing crazy. Okay, so I uploaded this reference sheet. This is the one we were working on. It has a bunch of stuffs. This morning in the shower, I was thinking of some other things that we need to put on here. So I'm probably going to do a page 2 of this, and I'll work on that this afternoon and try to get that uploaded. Things like Lewis structures and electronic structure, photoelectron spectrums, Boltzmann distributions, all those things. We'll get to that, Naya. Give me a second. We can look at question 1C. Yeah, like delta H for bond enthalpies. Yeah, that was another one. Thanks, Isaac. I thought of that one and hadn't written it down yet. Okay. Oh yeah, and then that was another one, was the periodic table. So I have a pretty good amount of stuff to put on page 2. If you guys come up with other stuff, we can throw it out there. Maybe as we're going through the 2019 exam, we might come up with a couple other ones. So this is our page 1, which I actually like the look of it. It's pretty clean. But you do want to make sure you kind of look over it to know where everything is. So I'll try to get my page 2 version. It'll take me an hour or two, maybe. Do that this afternoon, get that uploaded. Higher priority, though. I haven't published this yet because I'm still working on it. Thanks, Naya. Is I wanted to do a dry run of the AP test. So I'm going to publish these this afternoon. I haven't finalized the question yet, so I'm going to go ahead and show you guys what it looks like. So basically says, treat this like the real AP test. You'll have 30 minutes to answer question 1, which is going to be one assignment. And then you'll have 20 minutes to answer question 2, which is going to be a separate assignment. They are actually timed. There is a time limit of 30 minutes. I wanted to try to make it real and high stakes, kind of like the AP test is, so that you can kind of understand and get to feel what 30 minutes feels like when answering an AP Chem test. And so there, if I'm not mistaken, there should be a timer either on the side or on the bottom as you do this Canvas quiz. So I haven't put the question in there yet. So this quiz will be submerged in 30 minutes. Dun, dun, dun. Okay, so I'm going to put the actual question here. And then if you're going to copy and paste, you just copy and paste your response here. Or if you're going to upload files, you can upload multiple pages, 1, 2, 3, 4, 5, and then that's it. Okay. So, and then, oh yeah, at the bottom it has your time limit left. You might need to reload, Naya, if it's a little behind. So yeah, that tick tock on the bottom. So I'll put a real practice question here, and then I'll publish this this afternoon. And so I'll do one that'll take 25, 30 minutes, and then one will take 15 or 20 minutes. So I will be working on that this afternoon as well. So but I want you guys to do it over the weekend. I'm gonna wake up early. Yeah. So there'll be one that's kind of long, and then one that's kind of like a medium question, because they're doing one that's 30 minutes and one that's 20 minutes is kind of what the AP test has decided to do. So yeah. So again, let me go back to my quizzes. So I'll have AP practice test question 1, AP practice test question 2. I want you guys to do them over the weekend. So take, an hour sometime over this weekend, and maybe tonight, maybe tomorrow, maybe Sunday, and sit down and do it and treat it like it was the AP test. I want you guys to really kind of get in the mode, make sure you understand what it feels like in that high stakes with the timer going down. Yeah, I'll be in Discord this afternoon, Isaac, but I'll be working on this stuff, but I can also answer questions. So I'll be getting all this stuff ready to go. But yeah, I'm trying to think, do I have anything else to announce? If you haven't already, of course we have our modules here. If you haven't already checked out, I published all those links from what we were talking about on Friday. Yeah, that's fine, Isaac. So all these links, the PowerPoint testing guide, the YouTube walkthrough for the exam day, all these other stuff, the resources for the exam day, this is where all those hard copies are for everything. So check that out if you haven't checked that out yet. And then I also put my reference sheet here that you can download. as well as the periodic table. So you can either use your ptable.com or this PDF version of it, which is this nice and fancy one. Or you can really use any periodic table. Okay, so like I said, this weekend, you want to do the quizzes. I'll get those up as soon as I can, right after lunch. I'm going to try to kind of mosh together a question and make sure it's of an appropriate length. I'm going to try to guess on that. I don't know for sure if I can get that right, but I'm going to try to. But I wanted you guys to kind of feel what 30 minutes feels like and then what 20 minutes feels like, and then get used to the saving and uploading and doing all that stuff in a real chemistry question. So that's kind of my goal for this, and I want you guys to do it over the weekend, and then we'll talk about it on Monday. So Isaac wants to do the whole practice 2019 for response. So we'll get to that here in a second. Any questions about this this AP practice test question? You guys understand what I want you to do over the weekend? Okay, thanks, Maggie. All right, let's go to the 2019 free response test. All right, which ones do we want to do for 2019? Okay, ooh, lots of stuff. All right, so 7, 2F, 2G. So we want to talk about the scoring on 1C. And then questions on 2F and 2G. 3B and D. Okay. What other ones? Oh, 7C and 2B. So 2B, we'll probably do all of 7. 2C as well, or not C. Maybe we'll just do we'll just go through question 2. Okay. 1C. So Lauren has an actual question on 1C. Naya has a question about the way it's scored. So let's go through, and then we'll emphasize some questions. We'll skip over some other ones. 6CII. Maybe we'll do all of 6. Logan, we'll have to see. Okay. Let's go ahead and just look at this guy. Zoom in a little bit more. Okay. Question 1. So we have urea. H2N, CONH, widely used in fertilizers. Lewis dot structures given. Identify the hybridization of carbon. Easy. I'm going to put that on the reference sheet too. I'm going to do like a whole Lewis dots reference, like molecule structures, bond angles. I'm going to give you guys that on page 2 of my reference chart. So this question will be super easy if you have that. Urea is soluble in water due to its form of hydrogen bonds. You got to indicate hydrogen bonds. Easy, right? Ding, ding, ding. They just want you to draw one, though. So make sure in these drawing style questions that you always indicate just one of them, right? Make sure you read carefully the instructions because, yeah. Okay. So let's see. 5.39s dissolve in 5 milliliters and it's saturated. All right. Calculate the concentration of urea in moles per liter in the saturated solution. Okay, so let's do that. Actually, we can just shift this up. Okay, so up here, they tell us that it is 5.39 in 5 milliliters of solution. Okay, and then they give us the molar mass as 60.06. Okay, so the question asks us then, calculate the concentration in, calculate the concentration in moles per liter. So we can just do it as a fact label. How many moles of urea are in 1 liter of solution? 1 liter, 1,000 milliliters. 5 milliliters contains 5.39 grams. 60.06 grams is 1 mole. Oh, my wife just sent me a bunch of Instagram posts. All right, so 1 times 1,000 times 5.39 divided by 5 divided by 60.06. So we should get 17.9. Wow, that's really high. So 17.9 moles per liter. So Naya had a question about how this one was scored. So it says calculate the concentration in moles per liter. It says 1 point earned for the correct number of moles of urea, which may be implicit, meaning it may be implied, and then 1 point for the correct molarity. So what was your question, Naya? Let me scroll back. I saw it in the chat. It was earlier. Question about 1C is great. If you didn't write it in the moles, but we got the right concentration. Yeah. So that's why it says it can be implicit. Yeah, that's what they mean. That's what I mean. So, yeah. So if you do it in a factor label like this, the number of moles of urea is implied, and so you're totally fine because you have the right answer. Yeah. Okay. Any other questions? So you don't actually have to write it. No. But if you're paranoid, you can write it. So anytime they ask you to find a concentration, they usually have it broken down into 2 points, 1 point for the moles, 1 point for the concentration. Same thing on like titration problems. They always have them kind of broken down into 2 points, 1 point for calculating the moles, and then 1 point for calculating the molarity. So if you want to break it apart, you can. And that way you could maybe get 1 more point if you only got half of it right. But if you're confident in your concentration, you can just write the concentration. Lauren says to look over D. Okay. So the student also determines the concentration. So you don't actually have to write it. Now that's an interesting question. You do have to show your work, right? So you do have to have the work shown, right? You have to show what you're doing. Yeah. You do have to have your work shown. You can't just have an answer. So if you didn't have any work shown and you just had an answer, you probably would have they probably wouldn't have given it to you. So in any calculation problem, make sure you have the problem set up. Whatever you put into your calculator, make sure you have written somewhere. Otherwise, you might miss points. Okay. So let's look at D. Student also determined concentration of your saturated solution is 19.8 molar. Oh, they have it wrong. Oh, at 25 degrees C. Oh, they changed the temperature on you. Aha. No, you can do calculations in a calculator, but you have to show what you're doing. You have to set up the equation before you put it into your calculator. Based on the information, is the dissolution endo or exothermic? Oh, this is a cool one. Le Chatelier's principle. All right, this is a cool problem. So how does the concentration on D compare to our concentration of C? Is it more soluble or less soluble at a higher temperature? It's more soluble, okay? So we can think about urea solid going to urea aqueous, right? This is when we have a molecule just changes from solid to aqueous. There's no ions, there's no breaking apart, none of that stuff, just a plain old molecule, okay? So what we're thinking is, you can think about it in terms of Le Chatelier's principle. At a higher temperature, we have more aqueous. And so heat drove the reaction to the right. So we can think about if it's endothermic and heat's on the left, at higher temperatures, we add more heat, that shifts it to the product, we get a greater concentration of urea. So there you go. You can just use Le Chatelier's principle. You can say this reaction is endothermic because it is more soluble at a higher temperature. And it's shifted to the right. K becomes a larger value, all those things. I wonder what they said. There's so many ways to answer this question. They said the increased solubility of the higher temperature implies that the dissolution is endothermic. If saturated solution of urea is heated, then the equilibrium system is stressed. The stress is countered by the endothermic dissolution of more urea. Yeah, basically they're saying it shifts to the products because heat's on the left. This is kind of interesting though, because if you calculated C wrong and you calculated C as like 30 molar, they would have to grade D. Yeah, kind of both, Brand, but mostly it's a class for my high school kids, my high school AP chemistry class. But anybody that wants to learn some AP Chem stuff can tune in. Okay, what other ones? That was 1D. What other ones did you guys have questions on? Oh, that's entropy. Skip entropy. Entropy. Oh. I can highlight 76 messages. Okay, so we'll skip the rest of 1. If you guys have other questions on 1, we'll come back to it. Let's go to question 2. So question 2, says answer the following questions about halogens. Circular structure that has the longest bond length. Obviously iodine, right? Iodine because it's the biggest molecule. These are all single bonds, and so the larger the atoms are, the longer the bond length becomes. Yeah, Sammy, we'll get to 6. We'll do 6 and 7, I think, by the looks of it. Okay, so the other ones on this were B and C that people had questions on. Wait, you didn't have to do B. I told you guys to skip B. Yeah, skip B because B is electrochem. We didn't cover electrochem. All right, C. The boiling point of bromine is 332 Kelvin, whereas the boiling point of bromine chloride is 278. Explain this in difference in boiling point in terms of all the intermolecular force present between the molecules of each substance. Okay, this is a good essay style question that they love asking. So we're dealing with intermolecular forces. So whenever we're dealing with intermolecular forces of molecules, it's a good idea to draw the Lewis structures. So we have bromine and bromine. And we have bromochlorine, or whatever we want to call it. So they're both just single bonded, simple structures. Oops, too high. Okay. The other thing we could potentially think about here is, all right, well, what causes intermolecular forces? So apparently this one is 332, and this one is 278. So based on their boiling points, which one's stronger between Br2 and BrCl? Which one has stronger forces? Yeah, Br2 does, right? Higher boiling point, stronger forces. Stronger. Okay. Let's talk about the forces listed. This is a non-polar molecule, so the only forces here are London dispersion forces, or just dispersion forces. Right? Because it's non-polar, we only have London dispersion. On this one, we have both dispersion and dipole-dipole. Okay. I changed it when I switched over to Streamlabs. I might go back to the actual Twitch chat because the coloring is all screwy. So yeah, because originally I was capturing a Twitch window, and now I've used the built-in one into Streamlabs. I don't know if I love it. I might go back to capturing the window. I mean, it's fine with you guys being all pink, but I like the aesthetic of different colors better. You can recognize like different people easier. Okay, so back to this. So bromine is stronger. Now, typically, isn't dipole-dipole stronger than dispersion? So why isn't bromochlorine stronger than bromine? We've had a problem like this before. They love asking questions like this. So what we say is we say the greater mass, so we would say that the dispersion forces in bromine are stronger than the dipole-dipole and dispersion in bromochlorine because of the greater mass. That's what you say. You say bromine has stronger forces because it has a greater mass, and the London dispersion forces in the bromine is stronger than the combination of dipole-dipole and dispersion in the bromochlorine. How did they describe it? To see, they said the only intermolecular attractions in bromine are London forces, while those in bromine chlorine are London dispersion. However, due to the greater polarizability of the electron cloud, aka higher mass, the London dispersion forces of bromine are stronger than the combined intermolecular forces of bromine chlorine, thus the boiling point is greater. Yeah. So mass makes it more. Remember, mass and total number of electrons is a better way to say it, and polarizability is probably the best way to say it. When you have a greater mass and you have a greater size of your compound, more electrons, the molecule becomes more polarizable, which gives it stronger dispersion forces. Dispersion forces are based on the polarizability, aka the mass or the number of electrons. So a greater mass gives greater polarizability, which gives greater dispersion forces. So, yeah, 1 point is identifying the intermolecular forces in each substance. So this is easy. On this problem, if you just said this one has dispersion forces, this one has dipole-dipole and dispersion, automatically 1 point. And then if you correctly describe them, that's a little tricky. Correctly describing the intermolecular forces is a trick. Now, notice this is the second style problem I think that we've done on this. And they again asked a contradicting question. Right? Usually we learned that hydrogen is strongest and then dipole-dipole and then dispersion. But here again, they've done another example where dispersion is stronger than dipole-dipole. They like flipping the script on you and giving what traditionally we think of as weaker forces being stronger in a compound. So be aware and be careful because they love asking this style of question. They like having you understand that the weaker intermolecular forces can be stronger. Hi, Casper. Okay. Good. Let's see. We also had questions on C. Oh, that was C. Okay. And then F and G. Okay. So, oops. Yeah, you can. I think if you have your actual like username colored set, then that comes through. But otherwise, it just defaults everyone to the same color. I'm glad, KJ. All right. So let's see. We want to do a quick equilibrium calculation. 0.1 mole. Let's see. 0.1 mole is placed in an evacuated rigid cylinder. I think metallurgical materials engineering is really cool. I don't know a ton about it. Which one are you talking about, Naya? Oh, they want to do it in pressure. So they want you to calculate KEQ in terms of pressure. So remember, you can, whenever you're using gases, you're most likely going to be asked to use KP, which has you do pressures. KC you can do, but is probably not going to be the most worthwhile. Okay, so let me shoot this up a little bit. Oh, then I can convert the two for you, Naya, if you want me to. The equation to convert them is not that complicated. Okay, so let's look. You guys didn't have questions on D and E, so we'll just grab the answers for D and E. So they have the pressure of 1.22 atmospheres. They have the K expression of that. Okay, so our K is the pressure of Br2 times the pressure of Cl2 divided by the pressure of BrCl quantity squared. And we apparently have found that the pressure before equilibrium, the total pressure is 1.22. Okay, and then it says after the system has reached equilibrium, 42% has decomposed. Okay, so this is indicating of an ice table. So if we take BrCl, two of these, in equilibrium with Br2 and Cl2, we have our lovely ice table. Okay, so we said that if it was pure, it was 1.22 atmospheres. We know that this is going to be 0, 0, minus, now we got to be careful, this is minus 2x, right? Because of the coefficient, we have to take into account there's two of them that'll break down. So minus 2x plus x plus x. So 1.22 minus 2x, x, and x. And then the other information they gave you, they told you that 42% had decomposed. So if we take 1.22 and we times it by 0.42 to figure out what 42% of that is, 1.22 times 0.42, we get 0.5124. And so that means that much decomposed, which means we had 0.7076 remaining. Remains decomposed. Right? So if this much decomposed, what is x? Careful. What is x in terms of this? Is it 0.5124? Is x 0.5124? Divided by 2. Good catch, Lauren. Yeah, we got to divide it by 2, right? Because this is 2x. So that means x is 0.5124 divided by 2. So it's 0.2526. So if we just plug in Kp is going to be 0.2562 times 0.2562 divided by 0.7076 quantities squared. And we get 0.131. Hey, there you go. You guys figured out how to change your color. Okay, so I have 0.131 for Kp. Is that what they have? Ooh, they have a lovely, look at that. They have an ice table, so fancy. They have 0.13. Let's see, concentration, Kc. Kc relates to Kp. Wait, they should be the same. Oh no, but it's just divided by Rg, right? It's delta N over, now I have to remember the equation. It's delta something. There it is. Wait, oh, there it was. So Kp equals Kc times Rt raised to the delta N. So you just have to multiply by Rt. Well, you divide by Rt. So Kc equals Kp divided by Rt. So 0.131 divided by 0.08206 times temperature. What's our temperature? 298. You shouldn't need that, Isaac. So Kc is just K in terms of concentrations, and Kp is K in terms of pressures. So Naya, did you get 0.00536? And I do believe that is on the reference, right? It defines Kp and Kc. Yeah, it has it. It has right. It has Kp and Kc defined. Kp in terms of pressures, Kc in terms of concentrations. Oh no, Naya, why not? I'd have to see your work to give you more feedback. Let me double check my math. Yeah, no, it's 0.00536. It should be. Yeah, I don't know what you did. If they give you gases, just use pressures. I'd have to see your work. I'll look at it maybe later. Okay. If you don't know what you did, that's not a good sign. Let's see. 2, F, and G. Oh, G, we didn't do G yet. G says to calculate the bond enthalpy of the BRCl using delta H for the reaction, 1.6 kilojoules per mole, and information in the following table. Okay, so remember bond enthalpies, you have to draw the Lewis structures, but they're all single bonds. So we have 2 BRCLs going to, we have a BR, and a CL. And so they're telling us that this is our X, this is 193, and this is 243. So we just take 2X minus 193 plus 243, and that supposedly equals 1.6. Right? I was going to put bond enthalpies. Remember, with bond enthalpies, you add up all the bonds of the reactants and you subtract all the bonds of the products. It's opposite of heats of formation, where if you have heats of formation, you take products minus reactants. So 193 plus 243, negative, add plus 1.6 divided by 2, you get 191.8. Or just 192. Now, in terms of, remember, I kind of got onto Naya about showing your work. All you have to do is write this, and then you can write the answer, right? You just have to show the equation that you're solving when you put it in your calculator. I don't have to show all the algebraic steps. I just have to show this, and then I can show what the answer is. Which, did I get it right? Oh no, I have it wrong. Whoa, why do I have it wrong? Wait, what? Did I just type it in wrong? Oh, I did. I just put it in my calculator wrong. Shame on me. I would have missed a point because I just couldn't calculate it right. All right. So yeah, my algebra was right, or my math was right. I think I must have dyslexicked one of the numbers when I put it in my calculator. Always double check your calculations if you have time. Put something back in your calculator again just to double check it. Okay, let's see. That was 2. Let's hit 3, B, and D. I'm out of paper in my notebook. I'm going to have to start writing on backs of papers. All right. Question 3, B, and D. So B is a lovely picture. So let's put this on full screen so you can see it. So it says the student's given a 15 millisample of sodium carbonate. To determine the concentration solution, it mixes it with excess calcium nitrate, causing a precipitate. To balance the equation in the direction below, write the net equation of the reaction that occurs. Done. Diagram below is incomplete. Draw on the species needed to accurately represent the major ionic species remaining in solution after the reaction has been completed. Okay, lots of words. All right, so we have sodiums here. We have nitrates, sodium nitrates, and then we have calcium carbonates. If you write the net ionic equation, right, the net ionic equation should be something on the lines of oh, actually, never mind. Okay, so we don't need to do that. What? Yeah, no, just the math. On this one, the key thing that you need to notice in the problem is that the problem says we use excess calcium nitrate. So because we have excess calcium nitrate, what's missing from the drawing? What should still be floating around here? We got the nitrates. We got the sodiums. Yeah, we should have calcium ions. There should be calcium 2+ ions floating around because we had excess calcium nitrate. And so that's kind of the key, is that because we have excess calcium nitrate. Now, should we have any carbonates floating around? No, because the carbonates are down here in this precipitate. The carbonates are down here in the precipitate, right? So let's just double check. The drawing shows 1 calcium ion. 1 point is drawing a calcium ion, which their drawing here doesn't have one, but it should have a calcium ion drawn a calcium. Okay. Let's see, that was B. What was the other one? D. Droon. 2 more sodiums. Yeah, make sure you read the question carefully. That's a good point to bring up. All right, let's see. Determine the number of moles in the original. That's just a titration calculation. Let's see. D. Oh, this is one of these problems. I hate these problems. The reason why I hate problems like question D is because they're worded in a way that is so confusing, and you can get confused. You can flip it around and reverse it in your head really easily. So whenever you see like these style problems where they say like, oh, some student screwed this up, whenever they talk about an experiment being screwed up, just be aware that it's potentially tricky. So make sure you read those kind of questions very carefully. So this one, we got to make sure we read it very carefully. The student realizes the precipitate was not completely dried and claims that as a result, the calculated sodium carbonate molarity is too low. Do you agree with the student's claim? Justify your answer. Okay, so we've got a couple problems, basically. So first thing, the precipitate was not completely dried. What does that mean about the precipitate? Some of the mass is water. And not just some of the mass is water, it's heavy, Zach. That's a really good point. So the mass that we record for the precipitate, this 0.93 grams, some of it is water. Okay? So some of this 0.93 grams is actually water. So what that means is, that means that the true amount of calcium carbonate that we collected is less than 0.93. So maybe it's 0.7 or 0.6, okay? Claims of the result that the calculated molarity is too low. Now, if in truth we had less moles of calcium carbonate, what does that mean about the calculated sodium carbonate? Is it going to be too low? No, it'd be too high. And that's why these problems are so confusing, because it's like, oh wait, if this number is bigger, does that make this number bigger, or that number smaller? And you can always, like, if your brain works like this, right, you can always plug in theoretical numbers, and you could say, oh, let's redo the calculation on C using 0.6. If we did the calculation on problem C using 0.6, then we actually get a lower molarity. And so that would make the calculated molarity too high. Yeah, Maggie, that's a great way to approach the problems, because they are very easy to get confused. Let's see what they say. They said, disagree. The presence of water in the solid will cause the measured mass of the precipitate to be greater than the actual mass of calcium carbonate. As a result, the calculated number of moles of calcium carbonate and the moles of sodium carbonate will be greater than the actual moles present. Therefore, the calculated concentration of sodium carbonate will be too high. Okay. So 1 point for your discussion with a valid argument. I hate those problems because they're so easy to get backwards. So be careful whenever they talk about, a student screwed up the problem. Okay, let's do 6 and 7. Because a couple people had some questions about 6 and 7. You guys were good on 4 and 5? Oh, 5. Photoelectron spectroscopy questions, easy points. Easy points. Easy points. Okay, 6. Oh, what do we got? Look at these. I see 3 graphs. My brain automatically says rates. Rates. We're doing rates. We're talking about rates. All right, number 6. Nitrogen dioxide produces a byproduct of blah, blah, blah. Concentration, blah, 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 blah. All right, so we got this guy that's curvy. We got this guy that's straight. And we got this guy that's curvy. So I see 1 over concentration is straight. Second order, right? So here we go. Explain how the graphs indicate the reaction second order. Well, we have a linear relationship when we have 1 over concentration versus time, therefore second order, right? If that gives, and you could also talk about, you probably should mention that the concentration and the natural log of concentrations have curves. So you say this one's curved, this one's linear. And so because these are curved and this is linear, we can conclude that it's second order. Second order gives a linear relationship between 1 over the concentration and time. Write the rate law for the decomposition. Straightforward enough. Because it's second order, we just say rate equals K times the concentration of NO2 squared. All right, let's make sure that I'm not cheating the question here. Okay, the linear graph of 1 over NO2 versus time indicates the second order. Rate equals K times NO2 squared. Check. Okay. Let's look at part C and D. Consider mechanisms. Ooh, mechanisms. Okay. We didn't really go into mechanisms. We went over our review. So let's talk about mechanisms. So it says, consider 2 possible mechanisms for the decomposition reaction below. Is the rate law described by mechanism 1 shown below to be consistent with the rate law you wrote in part B? Justify your answer. Is the rate law determined by mechanism choose? Okay, so we got to see, are these rate laws consistent? Okay, so in this one, step 1 is the slow step, so that's easy. So we just say concentration of NO2 squared. So yeah. So because in this one, the first step's the slow step, we have our NO2 and we square it, it works. Right? Slow step is the one we want to focus on. That's the one that determines it. Now, letter 2 is one of the annoying equilibrium ones, right? So Roman numeral little letter 2, okay? So we would say that K, but it's still the same thing, kind of, okay? So remember, the rate is always determined by the slow step. So here, the slow step is in reaction 2, so K times N2O4, okay? But we can't, this is an intermediary, right? It doesn't appear in the overall equation. If we go back to our overall equation, right? So because N2O4 doesn't appear in the overall equation, we can't leave this in the rate law. And so what we do is we use this first fast equilibrium step, where we say the rate of the first reaction forward is going to be NO2 squared, and the rate of the first reaction reversed is N2O4. And because this is equilibrium, we can set these two equal to each other, right? And so we say K1 is NO2 squared, and that equals K minus 1 N2O4. And then what we do, we technically divide by the K's. The K's don't really matter too much. They go away. But the idea is now that we have this, we can take this and plug it in. And so then our rate is K2 times K1 over K minus 1 times NO2 squared. Now, they probably are just going to combine this all into a single K. Oops, sorry, screen. They're probably going to combine all this into a single K, which is fine. And you can do that too. You can just ignore the Ks. So again, let's recap. What do we do with mechanisms that start out with an equilibrium? With a mechanism that starts out with a fast equilibrium, you write the rate of the forward reaction, you write the rate of the reverse reaction using the coefficients as your exponents for your orders, set them equal to each other, solve for the slow step intermediary, plug in, and get the official rate law. So this one also agrees with the order that we found earlier. So they both agree. What do they say? They say, yep, step 1 is a slow step, therefore the determining step, calculated, which is consistent with the second order rate law. Yep, step 2 is slow, therefore it is the rate determining step of the mechanism. The rate law elementary is that because N2O4 is an intermediate, it cannot appear in the rate law for the overall. Because KEQ is this in step 1, they just plug it in. Oh, they did it. That's fine. And the rate law gives K times KEQ NO2 squared, which is consistent with the rate law part B. Yeah. So, yeah. You do have to show the algebra to say, you know, hey, I'm rearranging and plugging this in and I'm substituting in for the intermediate and I still get NO2 squared. So when we say it's an intermediate, what we mean by that is if you look at the overall equation, the overall equation is NO2 forms or breaks down into 2NO and O2. Okay, so this is the overall reaction. NO2 breaking down into NO and O2. If we go to this mechanism says, okay, that overall equation happens in 2 steps. First step, NO2 combines with NO2 to make N2O4. Second step, N2O4 breaks down into 2NO and O2. If we combine these two together, the N2O4 goes away, it cancels out, right? So it gets created in the middle of the reaction, but then it's gone. Rates really like gases, Isaac, and nitrogen compounds often have a lot of gases, or gaseous compounds often contain nitrogen. So, Lauren, does that make sense for your question? It's something that's created in step 1, and then it breaks down in step 2. So it doesn't actually appear in the overall equation. Yeah, we got time. We can do 7. 7. Okay. So student dissolves. All right. So this is a redox titration, right? So a student dissolved 0.139 gram sample of oxalic acid in water in an Erlenmeyer flask. Then the student titrated the oxalic acid with potassium permanganate, which has a dark purple color. The balanced equation of the reaction that occurs is shown by the titration above. Okay, so it's a 2:5 ratio. Identify the species that was reduced in the reaction, justifying answer in terms of oxidation numbers. All right, so we see the manganese here is +7, the manganese here is +2. It goes from +7 to +2, and so that means it gains electrons, which means it was reduced. I'm going to put oxidation number things on there. The reason I know that the manganese here is a +7 is because oxygen is a -2, and there's 4 of them. That makes -8, and so the manganese has to be +7. Manganese is +7 over there, it's +2 over there, and so it gains 5 electrons, so it was reduced. I think the carbon is what's oxidized. The carbon here is +3, and the carbon here is +4, so it loses an electron, so it's oxidized. Okay. Part B. The student uses a 50 milliliter burette to add the potassium permanganate to the oxalic acid. Here, we'll make this a little bigger. Oops. Until a faint lavender color was observed. Ooh. An indication that endpoint of titration has been occurred. The initial and final volume readings of the solution shown below. Write down the initial reading, the final reading used to determine the... okay, so this is just reading the burette. So you'd say... moles from the equation, Isaac. Moles from the equation. So initial is what? 3.35. Final is 29.55. So 3.35 going to 29.55. Oh, really, Isaac? Okay, 3.35, 20.95, and so the total would be whatever that subtracted, 26.20 milliliters. So write down the initial and the final, use the determinant that was added. Okay, so we wrote down the initial and the final. Given the concentration of potassium permanganate was 0.0235, calculate the number of moles of manganese ions that completely reacted. Okay, so that's just calculating the moles. So we just take the 26.20 milliliters times 1,000 milliliters in 1 liter. 1 liter is 0.0235 moles. Right, so we just do that quick calculation. 26.20 times, oops, yeah, 26.2 times 0.0235 divided by 1,000. Ooh, that's a small number of moles. 6.16 times 10 to the negative 4th moles. Is that right? Let's see. Yeah, 6.16 times 10 to the negative 4th. All right, and then the last one, part D. The student proposes to perform another titration. Will it manifest X moles in 1,000 milliliters instead of 1 liter? They shouldn't, but typically molarity is defined as the number of moles per liter. So if you do a something like that, Maggie, where you do a factor label like we've done, underneath it or to the side of it, I would put your final answer and say, boom, this many moles. Oh, you mean in the conversion? If you directly put the number of moles on top of 1,000 milliliters, that's fine. That's fine. That's fine. Sorry, I misunderstood your question. Yeah, no, that would be fine. Yeah, no one should get mad at you for that. If they did, they're dumb. But yeah, if you're ever writing molarity, you would write molarity as moles per liter. Probably, Isaac. That's close enough. They might be picky and might have. Oh, because your volume might have been different. Yeah, if your volume's a little bit different, then yeah, they should be totally fine. Okay, so the student proposes to perform another titration using 0.139 gram sample of oxalic acid, but this time using 0.000143 in the burette. Would this titrant concentration be a reasonable choice to use if a student follows the same procedure? No, of course not, right? This concentration is like 10 times lower, and so we would end up using 10 times the volume, or 260 milliliters, and our burette can't know that much. They are, but they wouldn't be on this problem, Isaac. It doesn't seem like, because they don't specify sig figs. So, of course, the answer is no. The 0.0043 is so diluted that the volume of the titrant needed to reach the endpoint would be much greater than 50 milliliters. Yeah, that's easy. So because the concentration down here is 10 times lower than here, it's like even more than 10 times lower. You would need 10 times as much volume, which the burette only holds 50. So... okay, whew, that's time. So I will work on getting those exams done by this afternoon. I will have them up and ready to go by 2 p.m. at the latest. And so then over this weekend, make sure you do that practice test on Canvas. Make sure you do that practice test as a good dry run of what the AP test is going to feel like. So it'll be good mental preparation to see if you really have everything and if you really are, where you are and what you're going to be do is conducive to the AP test. So I wanted to give you guys that experience. So that will be up and ready to go this weekend. Okay. Have a wonderful day, guys, and I will see you all on Monday. If you have extra questions, of course, drop by in the Discord. I will try to get that done this afternoon as well, Isaac. So I'm going to get, my priority is to get this practice test up and running. And then once I get that up and running, I'll get that cheat sheet working on. I should have it by the end of the day. I won't stop working today until I have that up and ready to go. So. Okay. Bye, guys.